Good day, I'm Maile Matsiba. Welcome back to our channel. We continue with our 2017 study guide of our CIR 113 module. We're looking at example 5.4.2. It says benzene and toluene are separated in a distillation column to yield a distillate of 95% benzene and bottoms products of 3% benzene. The feed contains 65% benzene and the feed rate is 100 kmol per hour. The reflux ratio is 3, that is LO over D is 3 on a mole basis, and it can be assumed that V1 equals to Vn. The question is, what are the flow rates of all the streams D, B, V1, LO, and Ln? And all percentages are on a mole basis and there's no chemical reaction. So, to answer such a question, as usual, we choose a basis, and the simplest base to work with is to choose the 100 kmol per hour of F because it's given. So we can just say basis 100 kilomole per hour of F. And with that said, we can go to our step 1. So now that we have our basis, we can actually calculate D and B. It's easy to calculate D and B because they all are external streams, or I can say, yeah, the external streams. F is coming in and D and B are leaving the system, so it's always easy to make a mass balance there. So let me just write it down. That calculate the flow rates of D and B. And for us to do that, we can do a benzene balance. If you can check here, we have the whole feed here is 100 kmol per hour, and we also have the mole fraction of benzene is called, we are told that it's 65%, 0.65, and we also have the mole fraction of benzene in both D and B. So the easiest way we'll do is to actually do a benzene balance. So we can just say benzene balance. We can just say, right, 0.65 multiplied by F is equals to, come here, we say 0.95 multiplied by D plus 0.03 multiplied by B. So we can continue further to say 0.65 multiplied by 100, because we know our F is 100, is equals to 0.95 multiplied by D plus 0.03 multiplied by B. So, and if you simplify further, it will give you 65 is equals to 0.95D plus 0.03B. Yeah. So we can just name this as our very first equation. So now moving further, remember we actually are calculating D and B, but for us to do that we needed to create equations. So hence we came up with the first equation. So now from here we are going to our second equation, and the second equation, for us to be able to get it, we're going to actually doing the mole balance of the whole system. Remember, initially we did the benzene balance. Now we're gonna be doing the mole balance of the whole system. So it's always easy to say F equals to D plus B, because remember F is coming in the system in one stream and then it's leaving in two streams. So F equals to D and B. So you can just write here that mole balance of the whole system. it's the mole balance of the whole system. We know that F equals to D plus B. Now, if you simplify further, we know already F, that is 100. So it's 100 equals to D plus B. And that gives us a B of 100 minus D. And that will be our second equation. So with that said, now that we have two equations, the first equation is this. We have two equations and two unknowns. This is the first equation that came out of the benzene balance, and this one is all the mole balance of the whole system. We can actually just make a simultaneous solution. We can actually calculate using a simultaneous system, and then we can get the values of B and D. And with that said, we can just say substitute 2 in 1, and with that said, we have 65 equals to 0.95 D plus 0.03. Now let me just bring that. I just want to highlight, I know it's high school mathematics, but I just like to make that emphasis. We already know that our B is 100 minus D. So now in this equation, on B, we're going to be putting 100 minus D. So it's 100 minus D. Then we have 65 equals to 0.95 D plus 3 minus 0.03 D, and with that said, it simplifies to 62 equals to 0.92 D, and therefore D equals to 62 all over 0.92, and that gives us a D of 67.3913 kilomole per hour. So that means that the flow rate of the stream here is actually 67.3913 kilomole per hour. And now remember that we actually are calculating the flow rate of D and B. Like this is actually the step that we're busy with, calculating the flow rate of D and B. Now that we have the B, we can just simply say from 2, remember this is actually the equation for B. From 2, we can just say B is equals to 100 minus our D. We already know it as 67.3913 kilomole per hour. And now if one uses a calculator, that gives us 32.6087 kilomole per hour. So that is actually our first step, where we're actually calculating the flow rates of D and B. Now this takes us to our step 2, where we're going to be calculating the flow rate of LO. This is actually LO. This is actually LO here. So let me just write it down. I'll explain it. Calculate the flow rate of LO. So with this said, now we have LO here. Well, it's related to V1 and D, but we already have D, and we also have been told about the reflux ratio. So we can just simply say, therefore, LO all over D is equals to 3. Therefore, LO is equals to 3D. That means that LO is equals to 3 multiplied by 67.3913 kilomole per hour, and with a calculator that gives us 202.1739 kilomole per hour. So that is actually our LO. And once we're done with the LO, we then move to our step 3. Let me just change the page here. Yeah, we move to our step 3, and in our step 3 we're going to calculate the flow rate of V1. Let me just write it down. Step 3, calculate the flow rate of V1. So let me just bring the page, the diagram, so we can, so this is actually our V1, and if you actually look at the direction of the arrows, you'll realize that V1 is equals to LO plus D. So, and we know that, okay, I can just write it down. Therefore, we know that V1 is equals to LO plus D. So we have already calculated LO and D, so we can either choose it to make it in terms of D or in terms of LO and D. So I'll just leave it as it is. I'll just use the path where we plug everything as it is there. So already we know that our LO is, let me just verify here. We calculated our LO to be, sorry about that. Let me just bring back my notes. Yeah. So we calculated our LO to be 202.1739 kilomole. So we can just say 202.1739 kilomole per hour plus our D, we calculated it to be 67.3913 kilomole per hour. And now with our V1, when you calculate the V1 and you use a calculator there, it will give you 269, sorry, yeah, let me write it properly, 269.5652 kilomole per hour. So that is actually our step 3, and that is calculating V1. Now we're left with our last step, which is step 4. So let me just write it down. Step 4, we're calculating the flow rate of LN. Let me bring the diagram again. So now we're calculating the flow rate of LN. This is actually LN, and if you look at the diagram, you'll realize that, especially the arrows, you'll realize that LN is equals to Vn plus B. So let me just write down that LN is equals to Vn plus B. But remember that we have already been told that we can assume that V1 equals to Vn, and V1 we've calculated it, and B we also calculated. So we can simply just express this equation V1 as Vn as V1, and then plus B, and that is equals to our V1 we calculated to be 269.5652 kilomole per hour plus our B, we calculated it to be 32.6087 kilomole per hour. Now, if you use a calculator there, it's going to give you ln of 302.1739 kilomole per hour. So this brings us to the end of the question, which is example 5.4.2. So thank you for your time, and I hope we meet again in our next video.